Hello and welcome to this video activity. So this video is meant to be played while you work through the global climate activity posted. Now this works easiest if you have access to a printer and you are able to print that out. However, if you do not have access to a printer, another option would be if you have two devices. Perhaps you could listen to the video on one device and read the assignment on the other device. That being said, some of you won't even have that, and it's okay to do the whole activity just with the video. That should be enough. What you will need is a piece of scratch paper and a pencil. Very, very important. So if you don't have those things, go ahead and pause the video and go find some. Okay, now I'm going to assume that everyone has their blank sheet of paper and their pencil, and we're ready to go. So I'm going to look and see what the lab says to do first. And it looks like first we need to answer the question, what is a desert and are all deserts hot? So I've gone ahead and thrown up a photo of a desert, but think about what deserts really are. They're places that don't receive a lot of precipitation, okay? So deserts are dry. And what do we know about water? Well, water is kind of a heat regulator. It takes a lot of heat to make water change its temperature, either to go up or to go down, okay? So deserts are dry, they're not necessarily warm. In fact, because they're so dry and they don't have water there to sort of try to keep them at a constant temperature, deserts actually have huge temperature fluctuations. So it can be incredibly hot, scalding during the day, but as soon as the sun goes down, all of that heat is just immediately irradiated into the atmosphere, dissipates, and it can get incredibly cold. And so temperature fluctuations in deserts are some of the greatest temperature fluctuations in the world. And that's because of the absence of water. So just again, the defining characteristic of a desert is that it has very little water, okay? It's not that it's hot. All right, next question, what is a rainforest? Oh, before we get to that, here's just, I thought I would show you a photograph of a cold desert, okay? So this does exist somewhere in the world. You can see an ice sheet there, a retreating glacier. Glaciers are much longer living processes. They're not from a single season. And so what's happening in that upper image is there's actually incredibly low precipitation, but when it does precipitate, when they do have snowfall, it automatically just freezes and it is able to stay for a long time because of those cold temperatures. Okay, so the next question has to do with rainforests. So I've gone ahead and thrown up a nice photo of a rainforest. What do you think the defining characteristic of a rainforest is? Well, hopefully you said it's somewhere that gets a lot of rain, right? In contrast to deserts, which get very little precipitation, rainforests get a lot of precipitation. So then the question is again, are rainforests hot? And the answer again is that's not what defines a rainforest. Rainforests are defined by the amount of rain that falls in them. So while we're most familiar with the tropical and subtropical rainforests, like the one shown in this image, there are also temperate rainforests, like shown in the above photograph, and they actually have these really close to where I grew up in Washington State in the Pacific Northwest. They're beautiful, not quite as hot as tropical rainforests, not as humid, but they get plenty of precipitation, and that is the defining characteristic of a rainforest. All right. All right, next up, we need to review low and high pressure zones. So, do you remember which one is representative of rising air? That would be low pressure. So, just to make sure we're all on the same page, I'm going to go ahead and sketch a low pressure system. If this is the ground down here, that's my grassy ground. And then I'm going to have an atmospheric pressure system. Low pressure system pulls air in along the surface, and then that air rises up and it heads out in two different directions aloft. So again, in along the surface, up, divergence aloft. I could add some more arrows here. And This is low pressure right here. This is the side view. And I'm going to go ahead and draw the top view in a different image. There we go. So I'll draw my top view up here. It's a low pressure system. That means, as we can see sort of down in this portion here, all of the air is moving in towards that low pressure zone. So we're going to go ahead and draw that, but we are going to make sure to allow those air masses to curve to the right. So I'm going to start with an upward facing arrow moving towards the low pressure zone. And there we have it. Now a high pressure zone, on the other hand, is going to have sinking air like so. And the top view of that, I'm again going to start with my up arrow, let it curve to the right, but this time the air is moving away from the high pressure at the base. So all of my arrows are going to move away, but curve to the right. And there I have both my side views and my top views of low and high pressure systems. So the next question is, which one of these is associated with clouds and storms? Hopefully you said this one over here, right? As this air rises, it expands, and that is going to mean that at some level condensation occurs and clouds actually form. So there's my nice little cloud that's formed because as that air rose, it expanded, which caused it to cool adiabatically, so no temperature exchange. This is all cooling due to an increase in the volume of the air parcel, and that causes the temperatures to decrease and decrease and decrease until they finally hit the dew point temperature, which is the temperature at which that air parcel is 100% relative humidity. It's the temperature at which it is saturated. It's the temperature at which condensation does occur. Okay, so now that we've reviewed deserts and rainforests and we've reviewed high and low pressure systems, we are going to take a step back and consider the globe as a whole and come up with a prediction for the global climate cycle. So to start with, you need to draw a fairly large circle on your paper, just as round and smooth as possible. It's supposed to represent the Earth, and I'm going to go ahead and draw the equator on mine. Okay, now the first question to ask ourselves is where on the planet it's hottest and where on the planet it's coldest. So give it a think. Hopefully you came up with the idea that it's hottest at the equator. I'm going to go ahead and write that down on my sketch. And it is coldest at the pole. Of course, there's 2 poles, so I'll go ahead and write that twice. And this is just because the incoming energy from the solar radiation, the sun's rays, is more direct at the equator, and it's coming in at quite an angle at those poles, and so that means that we have much more energy at the equator, much more heat than we do at the poles. But of course the Earth doesn't like to have this, extreme heat in one place and not in another, right? If you turn on a heater in a corner of a room, that heat isn't going to just stay near the heater, it's going to fan out over the whole room and try to equilibrate that room. And the Earth's atmosphere is going to do the same thing. So to figure out how that works, we have to think about what air does when it's warm or when it's cold. And well, hopefully you recognize that hot air, generally speaking, if it's warmer than the surroundings, well, it's going to rise. And that's actually what happens at the equator, is you have warm air rising. Now, what I'm about to draw in are actually the sort of global conveyor belt system of the atmosphere, and I'm going to draw it in 2 ways. The first time I draw it is going to be sort of incorrect. right? It's not what the Earth actually does. But it's what the Earth would do if it wasn't spinning. Remember how the spinning of the Earth leads to all sorts of interesting things like the Coriolis Effect, which causes everything to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. Well, that same spinning of the Earth is actually going to break up our convection cells here, but for simplicity, I'm first going to draw them in as if the Earth wasn't rotating, and I'll just do that on one side of my diagram, and then on the other side of the diagram, I'll draw in the real thing. So, if the Earth wasn't rotating, we would have warm air rising at the equator. It would go up, it would split off in two directions, heading up to the two different poles, and it would sink when it got to the poles, because that's where it's super cold, and that air would sink back down. And the conveyor belt system would bring the cold air back up to the equator. And you would have this sort of conveyor belt system of air rising at the equator, sinking at the poles, and just, traveling along the surface back to the equator again. Now, as I said, because the Earth is spinning, it turns out that the air just can't make that whole distance. It gets sort of messed up by the Earth spinning underneath it. And instead of one convection cell, it actually splits up into 3 cells per hemisphere. Okay? So on the left, I'm going to try to draw that, which is more the real situation. So I'm going to just for my diagram, I'm going to attempt to sort of split my cells up about 1/3 of the way around the planet. So those little ticks are going to help me do that. All right, so I still have rising air at the equator, and it's still going to go off in these 2 different directions, okay? We'll draw up to the north first. So in the first convection cell, it's like this, and you can see that this is kind of like a wheel or something, right? All my arrows sort of agree this could literally rotate. Okay, so when this air parcel falls back down, just like any high pressure system spreads out in both directions, when this air descends back to the planet and it hits the surface of the Earth, it's going to spread out in both directions, like so. And then it rises, goes over, and it splits up there, and like this. So, those are my northern hemisphere, and let's just go ahead and draw in the southern hemisphere. And do make sure that your little cells go all the way to the poles. Don't stop them somewhere crazy early. All right, so this means I have sinking air here. So this must be going like that. And if this is sinking, it must be pulling air in aloft. That air has to come from somewhere. And so we have like this. All right, so there I have all of my different global convection cells. All right, what's next? Okay, based on this, where do I expect to find rainforests and where would I expect to find deserts? Well, let's go ahead and label the high and the low pressure zones to start with. So everywhere that we have rising air, that's a low pressure zone. So here's a low pressure and low pressure. And there's a low pressure because this air is rising away from the surface of the Earth. Okay, now everywhere that we have sinking air, that's high pressure. So high, high, up here at the pole, high at the pole, and here's another sinking, so that's high. But these convection cells are actually supposed to be in 3 dimensions, right? So we can extend these areas out over 3 dimensions like so. Why don't I go ahead and show you this in sort of another diagram, and then we'll get back to my sketch in just a second. So here is just a cleaner version. It shows all the same thing that mine did. You have this rising air at the equator, sinking at the poles, and just going in a loop in all of these little cells. And they are 3D cells, which this image is sort of attempting to show you by letting it have this sort of three-dimensional thing. And that is to say that these cells are wrapped around the surface of the Earth. They're not off just to one side, they are above the Earth. Okay? Okay. So back to my sketch. This is actually one I did a little earlier. I'll go ahead and fill back in these bands. And I'll go ahead and re-list them as being, this is low pressure, high pressure, low, low, high, high. I'm missing this one almost, but that's a low and a high, and this is a high. Okay, so those are all labeled. So, based on this, where do we expect there to be a lot of precipitation? Where do we expect to find our rainforests? Well, as you know, anytime that we have rising air, that can lead to rain. So everywhere that we have a low pressure zone here, those are going to be our possible rainforests. So I'm just going to sort of draw that in as a green band in this general zone. All of this we expect to be rainforest. And same with our rainforest over here. Everywhere that we have rising air, we expect to have a rainforest. And conversely, everywhere that we have sinking air, we expect to have deserts. So we might have our latitudes a little bit off, but our pattern should work. Patterns of rising and sinking air, rainforests and deserts. All right. So at this point, we have all of our high and low pressure zones labeled. We have all of our rainforests labeled. For me, the rainforest is in green and the desert is in this yellow color. So I'll just write that down, desert, rainforest. Okay. Now, like any good scientist, we need to check this against data. So let's go ahead and see what that looks like. Here is a plot of annual average precipitation globally, and we should see a few things, right? So first off, here are our tropical rainforests. That comes out pretty prominently, but you can also see, especially in the southern hemisphere, you have this secondary rainforest band, okay? And you can kind of see it up here as well. All right, now as for our deserts, the polar deserts are standing out loud and clear, right? So it's a desert at both poles. And we do also have that sort of in-between desert as well. So again, desert, rainforest, desert, rainforest. We have this same pattern just like we did in our initial sketch. So back to our original sketch, and the next thing that we need to do is draw in the surface winds. And that's going to be not too bad as long as we remember that the surface winds are the ones that are down near the surface of the Earth. So we actually already have a key on here trying to tell us what direction these winds blow. And to start with, let's just look right here. The bottom of this convection cell has winds blowing northward. So that tells me that all the wind in this entire band here, in between there, is going to be blowing northward. But I also know that the Coriolis effect is going to have an influence on those winds. And so what is going to happen is that they will blow north, but they will deflect to the right. Okay? Now, the winds in the next band up, those ones are blowing towards the south. So I have to draw arrows pointing southwards and to the right. Now, if that doesn't look like it's bending to the right to you, go ahead and flip your globe over till it's upside down so that you are drawing those arrows in the up direction, and then when you curve them to the right, you should see that they actually do match mine, okay? So, next band down here, air is blowing towards the south, so my arrows are southwards and to the right, southwards and to the right, southwards and to the right. And in the southern hemisphere, we have some winds blowing towards the north. And in the southern hemisphere, things curve to the left. So my surface winds here are going to be to the left, to the left, to the left. And in the next one down, they should be to the south. So to the south, to the south. And then I should have this tiny bit here. Oops. Yeah, they should be blowing to the north and to the left. Okay, so there I have all of my surface winds, and once again, I need to compare that to real data and see if I'm in the ballpark with how I feel the winds should be. So here is a map of global winds averaged again, and we can see a few similarities, right? So if we remember, winds here were blowing in this direction, and there seems to be fairly good agreement. And above that, over here, it was like this. And let's see, down here, it should be like this. And up here, these look a little different because we have them drawn like this, but they're still blowing sort of towards the east there. So overall, this does agree, but something sort of gets in the way, right? The continents here. Let's see if we can. These are messing up our wind, and when you think about it, if you go and you look back, these continents messed up our precipitation patterns too, right? So it turns out that our prediction for the global wind patterns, shown again here, actually agrees pretty well with the global climate. And if there weren't any of those pesky continents to get in the way with their different specific heat and their different elevations, then what we've drawn here would actually be very indicative of global climate. Now, continents do exist, and they do heat at a different rate than the oceans, and they do have mountains that will force air up and over them. So it is a little bit more complicated. To see exactly how that plays out, we are actually going to go look at some current weather data in the next video. So double check your sketch, make sure you understand exactly how to draw this, try to draw it without the video and see if it makes sense to you. Really, it's all just based on the fact that the equatorial regions receive more heat than the poles, and the planet's just trying to equilibrate itself to spread that heat around and try to be as productive and as equilibrated as possible. All right, so I will see you in the next video to look at some live weather data from a really cool perspective.